As you can see in the title of the topic, I'm going to talk about chaos and chaotic motion in a microsystem, which we use for engine mount. Engine mount means there are some devices, usually 3 or 4, to isolate the vibration coming from engine to the body. There are several different type of engine mount. I'm going to talk about basic and then the requirement and then some intelligence that we add to engine mounts, and then talking about the problems. And one of the problems would be chaos. For vibration in simple mode, simple talking, we need a base which is excited, and then a mass, and then some isolator. Isolator is usually the simple way, the spring and a dashboard. And it is supposed to work against the gravity. These are normal or very cheap vibration isolator using as engine mount. I don't know, maybe they are $5, $6, $10, and more advanced maybe $15. But they are not doing what we need. This is a sandwich of layers by rubber and metal, which is normal. Majority of cars are using this. But let me show you what is the requirement to make it more intelligent. This is some simple mathematics that we go to absolute displacement, relative displacement, and absolute acceleration. There are 3 items that we are going to use for optimization. I will talk about that briefly. As a sample, here you can see the simulation of a vibration isolator. Hopefully it is working. Please. It is. Okay, a base is vibrating and a mass, which is supposed to be isolated, goes through a frequency sweep. And as you can see, for example, if the vibration is 1 unit, depends on what is the frequency of excitation, the actual mass can go beyond 1 unit or whatever is the unit of excitation. So this is a normal problem with linearity. Take a look at the frequency response. Here you see acceleration response of this mass. If we assume that from here, which is the node, to the left is low frequency, and after that is high frequency excitation, at low frequency, as you can see, we need a very high damping. This line is high damping. Zero damping goes to infinity at natural frequency, as you know. And after the node, what happens is that we need a very low damping. So we need a system to be smart to switch between very high damping to very low damping after a specific frequency of excitation. That's our requirement. Same situation with displacement transmissibility. So what is the solution for such a requirement? Let me move, instead of talking about low frequency, high damping, high frequency, low damping, let me switch the problem to amplitude. If you look at this area after resonance, what happens is that after resonance we get high amplitude of excitation. So high amplitude, we need high damping. Here we get low amplitude, and in low amplitude we need low damping. So we are switching from frequency damping relationship to amplitude damping relationship. Reason is that frequency is not detectable easily unless we have a continuous vibration, but amplitude is detectable instantly. So that's what we are going to do. Question: can we take advantage of nonlinearity to design such a system? The system is going to be smart, but it is going to be passive, means it's going to switch between high and low damping by itself. We are not going to use any computer. That's the whole purpose of that, to make it cheaper. So far, this is what we found, that high damping at low frequency, low damping at high frequency. I already switched the frequency dependence to amplitude dependence. As you can see, there are two answers or two solutions so far. One of them is called piecewise linear suspension. The other one is hydraulic mount. And I'm going to explain that these two are supposed to do this switching. Let's go here. This is the piecewise linear vibration isolator. This is the mass, for example, the body, and here excitation from the rod. And this is the main suspension. There is another suspension, secondary. This is primary. There is a secondary. The secondary is not going to act at all as long as the amplitude of this guy is very small. So when we have amplitude very low, we have this damping, which is low damping. When the amplitude is supposed to be high, it reaches the gap and the secondary system is going to be engaged. When the secondary system engages, we have two dampings as well as two springs. So what we have is at low amplitude, low damping, high amplitude, high damping. Promising, it looks working. This is a sample of practical system, for example. Low amplitude, just one spring. High amplitude, secondary spring, and we can add damper as well. The second solution is hydraulic engine mount. Engine is here, the body or chassis is here, and this is a rubber which carries the load of the engine. But we have a chamber, the upper chamber, lower chamber, between these two chambers, which is filled by oil. Oil can go from this tube, a tube goes from upper to lower chamber. The tube is very narrow, so it gives a high damping. Also, there is a big hole between the upper and lower chamber. So if there is a big hole and a very small hole, like orifice, like this tube, when engine is vibrating, the oil goes through this big hole up and down without any damping. But the smart people implemented this device, which we call that decoupler. There's a plate in that hole moving up and down with oil. At low amplitude, it's moving with oil up and down, no damping, and oil is going between these two, so the damping is low. But when the amplitude is high, this decoupler closes the hole, so prevent any oil goes back and forth between these two. Oil must go between the two chambers through that tube, which gives us a high damping. So another system that gives us very low damping at low amplitude, high damping in high amplitude. It looks good, but the problem is not that easy. This is what you see in the decoupler action. There are some other system with different company. The one that I showed was probably from Nissan, a couple of models that we disassembled. But anyway, other companies are using 3 chambers, 1, 2, 3 chambers with this device. Also, there are a variety of different invention to force the oil to go through this big hole and so on. We call that bell, not important. This is another one, but this is one of the actual one that we bought for experiment, and we cut it. As you can see, this tube here goes between upper chamber and lower chamber, and this is the decoupler, as you can see, which is going to vibrate. The vibration limit is less than 1 millimeter. This is another one, a more expensive one. Lower chamber here, the upper chamber, decoupler over there. This is what we measure actually, P1, P2, P1 minus P2, which is the pressure difference between upper and lower chamber. And as you can see here, pressure difference is 0, means the decoupler is moving with oil, so oil is going through the big hole and we don't see any pressure difference. At this part, the decoupler closes the big hole and the oil must go through the tube. As you can see, the pressure difference is huge. And then open, close, and so on. Around 2006, I introduced a mathematical equation to go to the vibration system to simulate the same action. This is the response based on the mathematical analysis, and it simulates the same behavior fantastically. So we use that. Of course, there are some mathematics, I skipped that. This is the frequency response of the system based on perturbation analysis that we have done. The rest of them are here. Using perturbation analysis and the equations, of course, we can find the frequency response and do sensitivity analysis, find the jumping phenomena, and so on. This is out of our scope today, but I want to mention what is the difficulty of the analysis, mathematical analysis of the system, and the behavior that we cannot predict all the behavior of the actual system using mathematics. This is what happens. If the system was linear, the only thing that you see are plotted here, and you're familiar with that. Let's assume that at this point, which in this case is 2, we have the limit, either piecewise linear or the hydraulic mount. The amplitude goes at this point, then the damping and the stiffness is going to be triple or any number of order that we wish. Instead of following this curve, at this point we go to that curve, and then we come here and we continue. If you are familiar with nonlinear system, as you know, it goes up to this point and then jumps down and follow increasing the frequency. By decreasing the frequency, we are going to move from A to B, jump up and follow this and come back. Looks good. But there is something which we have to notice. The notice is this. Let's assume that amplitude is high enough that we have engagement. Now in that frequency, what happens? We have this engagement, so 2 damper, 2 spring, and then during one cycle of motion, we go from high damping to low damping to high damping, back to low damping. So one cycle is a combination of low damping, high damping. It is not just on high damping. This affects the whole system. Here we can compare, the effect of introducing secondary system. This one belongs to ordinary system. This one belongs to first and secondary system. And as you can see, if you design the secondary system badly, the behavior of the system is even worse than without that. So there must be an optimization process. Here is the optimization process. And as you can see, yes, this is the previous one, which was badly designed. This is after tuning the system to eliminate the jump phenomena and then reducing the relative displacement. So optimization has been done, but there are some other problems which I'm going to talk about. The problem is very low amplitude, jump, noise, heating. The second one has jump, frequency island, then asymmetric behavior and nonlinear spring. And let me just mention one of them, which is frequency island, a phenomenon that we discovered around 2009. Very interesting phenomena when we have the gap size close to the peak value of a linear system. So the primary system is barely or not touching the secondary. But because of some excitation, for 1 second, or one fraction of time, it touches the secondary, but it's not going to let it go. This is what happens. So the system is supposed to vibrate between these 2 points. This is the amplitude. At this frequency, because of some sudden excitation, it jumps to an island and it keeps vibrating there. Very interesting phenomena, which we published several papers based on that. This is the nonlinear behavior, and as you can see, the gap size is going to be increased up to the point that it is barely touched the maximum linear, and then frequency island appears, and then if we increase the gap size, frequency island is going to disappear. Okay, that's again out of my question. let's back to the original system. This is the rubber material, and this is the metallic part. The engine is here. This is the actual behavior of the system by experiment, and also the continuous line comes from finite element analysis, very nonlinear string. Based on elasticity, we define this equation. I want you to remember K1, K2, K3. K1, K2, K3. K3 is the coefficient of x, x squared, x cubed. The effect of the variation of these numbers that we measure in lab affects the system. The system becomes nonlinear, and these are K, F, and so on. Some non-linearization comes to the picture, and we introduce finally three equations. One of them here in two lines, which is displacement of the actual engine. UD, it is decoupler motion, and UI is the inertia tract. Inertia tract is the mass of the fluid that is going through the tube. Three equations, and frequency analysis goes there, but let's check the equilibrium of the system. The system is nonlinear, so it gives us some interesting equilibrium behavior. Of course, when you have the equilibrium point, you have to check the Jacobian matrix to find out if it is stable or unstable. But what we have based on these data that we measured in the lab, this is equilibrium for S1. What is S1? Let's get back to see S1, S2, S3. S1, S2, S3 are the same that I introduced to you, K1, K2, K3, with a non-dimensionalization. So what you see here is we are testing the equilibrium of the system with the effect of variation of S1, which is very stable. There is no problem. At some range, we get two equilibriums, so it must give us some bifurcation. This, as you can see, variation of S3, or a test for 1 point of S3 equal to that value, it gives us a stable point. The other one, S3 negative, another stable point. But when S3 is varied, when it goes to negative, we get a bifurcation, which Jacobian is going to show that these 2 points both are stable. This is going to be unstable. You are familiar with that. And this is the bifurcation plot for variation of S3. But when we try to change S2, remember S2 was the coefficient of x squared. X squared has a strange effect. And as you can see, this is bifurcation plot, variation of S2, and these are equilibrium. Let's magnify this part and put it here, and as you can see, chaos is happening here. Next step is to go for fast Fourier transform and autocorrelation function and Lyapunov function, double check to find the chaos here, and then create the same chaotic motion in the lab. But in the lab, we don't get easily the behavior that we predict here because we ignored friction, which is affecting negatively in introducing chaos. But anyway, this is the result that shows that there is chaos for our system, and the next step would be better analysis. Thank you very much.